To all the committee for inviting me to do this. I'm very pleased to be here. And I was just watching the names of people joining, so I see that there are several friends who've joined already. It's great to see you as well as everyone else. Great. So what I'll be talking about today is stuff that I've been working on for the last 10 or 15 years, although I did some preliminary little bits even earlier than that, trying to develop luminescence chronologies of sediments to understand active tectonic contexts. And lots of different people have contributed to this, but in particular, James Dolan, Russ Van Dissen, Sally McGill, Rob Zinke have made a really big impact on the stuff I'll be talking about, and also the work that I've done with Richard Walker and his group at Oxford. Great. So let's move on to the next slide. So I'll give a quick introduction to luminescence dating, at least as I see it. I'll talk a bit about something called post-IR IRSL, which I do on single grains of potassium feldspar, and there are various different ways that we can do that. I'll talk a bit about those. IRSL, by the way, is infrared stimulated luminescence. We'll then talk about some applications in New Zealand and California, particularly with James Dolan's group, and ending up with a paper just published at the beginning of this year. And then I'll talk a little bit about what we're going to be doing in the future. In particular, the latest stuff that we're doing uses a form of multiple elevated temperature, or MET IRSL, and we're also quantifying single grain histories, which is something that's come from our work on understanding sediment dynamics. I saw Anne Gears was in the list there of people that were joining, so hi Anne. We'll be talking about some of the stuff that overlaps with your work as well. Great, and I'll just say a little bit about the conclusions. So here are the kind of take-home messages, if you like, from the talk. So both quartz OSL and K-feldspar IRSL work really well when they're working well. That's kind of circular, I realize, but the question is, can we make it work well? Can we know when it's working well? So the examples I'll show you, I feel that it is working well, and it gives us the opportunity to find out something new about how faults operate, and I'll talk about that, and the irregularity of slip-on faults. What I find from my experience of doing luminescence dating for several years is that it's quite iterative, and sometimes the things that are uncertain are not the things that we always focus on. And usually this emerges when we have sufficient data to be able to see that. And this is something I call data density. There's something I call the data density threshold. It's basically when you have enough data that you can see how good your data are. So it means that's quite a lot of work, but I think that's quite rewarding. Finally, I'd just like to say, I find it extremely rewarding to be working on something where we can use the surface and the surface record, particularly sediments, in order to try to understand deep earth processes, tectonic processes. Okay, so very quickly, luminescence dating basics. The signal that we measure is a signal which is produced by radiation-induced trapped charge. That trapped charge builds up through time when grains are buried in the environment from the sediment around. That population is reset by either heating it, and that's the basis of people who do thermoluminescence dating, for example, of ceramics, or it can be reset by light exposure. And optically stimulated luminescence, optical dating, IRSL, these things work well when the signal is reset by light. The sort of amount of light we need is from very short amounts of light as short as 1 second for quartz OSL in some circumstances, up to much longer. 10 to the 5 seconds is approaching a couple of days. Okay, the age range we can date something like from 1 year back to about 200,000 years, with an uncertainty of typically between plus or minus 5 to 10% at 1 sigma. We calculate the age by dividing a dose that we measure in the laboratory by a dose rate, which has many components, and we measure it in different ways. So the signal that we measure when we do OSL or IRSL dating, we hope, will be the signal that has built up since the grains that we're measuring were last exposed to light during their transport prior to being deposited when they were moving through the environment in the natural circumstance. The signal that we measure is stimulated by using light, and that helps identify traps that are sensitive to light. And that was the basis of the thinking of Dave Huntley when he first developed optical dating in 1985. Well, it was published in 85, so I guess they developed it over the couple of years prior to that. Okay, up at the top right, that's what a quartz OSL signal looks like, a very rapid decay when you turn the light source on, and a sort of flat, stable background that we can measure at the end. So some of these images come from a paper I wrote in Annual Reviews of Earth and Planetary Sciences back in 2011. Okay, so the good thing about luminescence dating is that the material is ubiquitous, quartz and feldspar grains, and the signals we look at are really sensitive to ambient conditions. So you don't need much for the signals to change. Unfortunately, that's also the kind of weakness of the system, which is it's very sensitive to ambient conditions. And that includes when we're collecting it in the laboratory, but also things like issues such as thermal stability. Slight differences in environmental conditions may be having an impact. There's also a large number of parameters we have to calculate, which makes it complex, and there is a lot of intrinsic material variability between the different minerals that we measure. These two main systems, quartz OSL, which I think of as like a digital system, when it works really, really fantastic. So it's like a really beautiful, clear digital radio, really clear. But if it's not working, it's not working. Whereas feldspar is kind of like an analog system. So it's like an old radiogram, and you kind of have to tune it. And if you've tuned it right, it can be really good, but it's kind of a little bit crackly. So there's a kind of little summary. We can have a model over here on the left of trapping sites within quartz. This is a numerical model developed by Richard Bailey and taken forward more recently by other people. And it simulates the behavior of quartz OSL really quite well. And on the right is a model which you can see is rather different in its shape, developed by Jane and Ankergaard back in 2011. And there are some modifications to that now. But feldspar has this kind of analog feel to it. Everything's a bit variable. There's a wide range of different signals. They're non-first order, which makes them harder to both model and measure. But we have the potential to tune it. And that's really one of the great advantages of feldspar IRSL. Okay. So discovered by many different people, I think I saw Marcus Fuchs was there as well, and Marcus has certainly worked on some aspects of this. Frank Preusser did as well, is that in many mountainous and active tectonic settings, quartz OSL signals are very dim. So where I'm working in California or New Zealand or High Asia, then we really tend to need to use IRSL to overcome this problem of dim quartz. The way I'm currently making measurements in let's call it benign circumstances where conditions are good and everything's working well, is using something called post-IR, and that makes two IRSL measurements, and we use the second one, hence the name. So it's an IRSL measurement that's made after another IRSL measurement. So that's step 4 on this sequence of different measurement steps that we do. At the end of each of these so-called single aliquot regenerative dose cycles, we measure the sensitivity of each grain if we're doing single grains, or each aliquot if we're doing different aliquots. So I'm not going to go right through this in detail. Feel free to stop the video and have a look in more detail if you'd like to read more detail. Okay, the measurements I make tend to be done on a RISO machine similar to the two at the top here that are the black boxes. There are also equipment made by Freiberg Instruments, the Lexig Smart, for example, and people who use that say it's great and works well as well as the RISO set. So typical measurements take something like 24 to 48 hours per sample on one machine, and that's one of the factors that slows us down a little bit. Okay, I mentioned that we rely on light to reset the signal. In many circumstances, I think you can imagine that we don't always have sufficient light that all the signals in all the grains were well zeroed. So to do that, we can use either single grains or small aliquots and take the minimum values from each of those that we measure, and that identifies those grains or those aliquots where the grains were well zeroed. Where quartz is insensitive, then using feldspar has now been developed to work really quite well. So we mount single grains in holders such as these over on the right, 1 centimeter diameter disc with 100 little holes in it. They're 300 micron holes, and I'm putting roughly 200 micron diameter feldspar grains into those. These are actually photographs, I think, these may be taken from Jeff Duller's work, if I remember. I can't actually remember where these photographs came from. So at the top, you can see I'm plotting these on these kind of square plots. Some people use radial plots. I find the square plots easier to understand. You can see the apparent age for these different single grains plotted in order from the most sensitive grain to the least sensitive grain. There are various reasons to do that. I won't go into those at the moment. And then we can take those that are statistically internally compatible with each other at the minimum value. So those are the ones colored red. And the top sample is an example of a sample that's well bleached. And the bottom is a sample that's poorly bleached, but we can still derive an age from these minimum value. It's just a lower percentage of grains. We had the opportunity through SCEC funding starting about 10 years ago to test this approach, post-IRAR, on a beautiful site called El Paso Peaks that had previously been worked on and is published by Dolan et al. And what's great about this is it has a really excellent C14 age control going back 5,500 years. So we re-excavated it back in 2011 and collected a whole series of different samples. It's a small player lake right up against the Garlock Fault in California. This was my master's student, Belinda Roeder from UCLA. And if we look just at the IRSL of the top couple, actually not the top couple of samples, but samples up near the top, you can see that those agree beautifully on this oxcal plot with the radiocarbon ages on either side. So the ones in red are IRSL, post-IRIR, and the other ones are the C14 ages. Okay, at the other end of the spectrum, we were able to get samples that had been independently dated using beryllium-10 profiles. This is an example of samples that came from Mongolia. Ed Nissen wrote these up. And the samples had originally been worked on by Morteza Fatahi in Tehran, and he was very kind to provide me with some of the material, and then I remeasured those at UCLA and got an age that was in surprisingly good agreement with the beryllium 10 ages. And we were able to do something similar on another project that I had working in Baja California with some slightly younger material, 30 and 50,000 years old, respectively. And we now, this image actually it dates from 2019. This is a paper by myself and Rich Walker as a book chapter in a book on luminescence. And there are 34 samples on this plot where we compare the post-IRIR IRSL age versus independent age with different types of control. So C14 control for the green and the red, and beryllium 10 profiles for the ones in blue. And you see it really agrees very nicely from about 300 years back to 80,000 years. Okay, let's talk now about the application to active tectonics. I'm going to talk, first of all, about samples from New Zealand, from the Marlborough Fault System. If you've heard of the Marlborough region, it's probably because of the very good wine that's grown in this region, including the Arrowtree Valley, which is a major valley with defined by one of these parallel or subparallel strike-slip faults that make up the Marlborough Fault System. So the sites shown by those stars are sites where we've been working. This is a project initially funded by the NSF to James Dolan and myself with Russ Van Dissen. And then subsequently, we've had another project that involves the same team with Tim Little as well from Wellington. And we've really got quite a nice body of data. So I'll talk about this site that you can see on the left, the site of Branch River, and you can see there the Wairau Fault running across a whole series of fluvial deposits that form a kind of fan where the Branch River joins the Wairau River and has been gently down cutting by about 10 to 15 meters or so over the last 10,000 years, something like that. And it has given us an opportunity to look at the slip rate. And we have similar sites on these different subparallel faults. Okay, this is what it looks like on the ground. This is Branch River. That was the area we were just looking at. There are now far more trees planted than that photograph, which is an aerial. The photograph I showed you a minute ago was an aerial photograph from the 1940s. And to aid with the farming, they've planted windbreaks and lines of trees. And there's largely, this is cattle that wander around on here. So we're able to go across the surface. The landowners are very supportive, and we can dig holes at different locations in order to collect samples. When we look down the holes, this is what we see. We see terrace sediments. In this case, it's just sandy, but typically there's gravel in there as well. And then overlying that, we have a sandy silt or silty cover. And we usually collect samples in that to date that as well, because we want to understand the full sequence of sedimentary environments that are developing that we're dating in this pit. Okay, so these are nice diagrams put together by Rob Zinke for the paper. This is actually one of the later papers on the Marlborough Fault System that we wrote. So this paper came out in 2021. And the diagram at the top right sort of explains the geometry nicely. So we have the Wairau Fault, which is a strike-slip fault, and it has offset these different units. And in general, the lower the letter, the older the unit. The exception is that unit W is older than unit A. And the bottom two diagrams show restored margins of those different terrace units that are colored in different colors. So you can see it's a really beautiful record. And we can basically go anywhere that suits us and dig a pit. It's actually quite tricky deciding exactly where is the optimal place. Another feature of these kind of situations is that not only do we rely on the terrace riser, that is the break from one terrace level down to the next terrace level, the terraces themselves have multiple features within them where we can clearly see an offset of those features. So we are less reliant on worries about whether we should use an upper terrace or a lower terrace reconstruction. We can actually date the terrace unit that includes those offset features. In the future, there's the potential to actually try to distinguish between different features on the same terrace, but so far we haven't really done that. Some of the other features that look offset are actually coincidental things that are to do with the way that the farmers have planted the hedgerows. Don't worry about the larger apparent offset. That's not really an offset, just happened to be parallel. It's interesting as well that the road kind of looks offset, but we believe that that's not real. I mean, they just built it to go down the little hill there. And you can see the amount of offset here goes from 26 meters up to 58 meters. Now, here's another example from the same project. This is the Arrowtree Fault at a place called Saxton River. This is at an elevation of 1,000 meters up the end of the Arrowtree Valley. Again, this is a large river over here on the left with a strike slip fault running across it. The bedrock has quite a large offset, and then as these terraces get lower and younger, and note that the numbering system follows the American system of starting the terrace numbering with the oldest unit, then you can see that the amount of offset gets less. The green dots are the places where we dug pits. We dug these pits by hand, and it doesn't take too long, particularly when you have Russ van Dissen to help. He's very good, particularly with the breaker bar. So we were able to dig down into the gravel, and that on the bottom right, you can see that picture looking down. You can see the aluminium cap that I'm hammering into the gravel. In many cases, the gravel is quite soft, and we can simply push into it between different cobbles. And we also developed a couple of techniques for getting behind cobbles where it was a coarser texture. Okay, these are the ages that we were able to produce from that site, Sexton River. I think there are 34 ages here at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 separate pits, up to 5 samples in some of the pits. In other pits, just a couple of samples. And the age estimates that are colored in red are either where we've gone into silt, shown in yellow on the little stratigraphic diagrams, that was significantly younger than the terrace, or in some cases, it's the older gravel, which is significantly older. And what we've dug down into an island of older gravel. So an example of that is the pit that is called 1420 on terrace T2B. I think you can see that age is about 7,000 at the top and then about 15,000 at the base. And those are things that we can't recognize simply by looking at the stratigraphy. The difference in the gravel is so small that we aren't able to tell it. There's a lot of variation. Okay, now what do we do with this? Well, we put that into a Bayesian model. I'll come back to talk about that. I wanted to quickly show you what the single grain age data look like from this site. And so here are some different examples. And the number of grains that gave us a signal, you can tell by the number here on the right. So you can see I really measured a very large number of grains. I measured 600 from this site, this sample in the middle, J0859. And of those 600, 175 gave us signals, and of those, 108 were consistent with each other at the minimum value, and that's 62%. So that's really very well bleached. So we were surprised how well bleached the signals were from this site. Okay, so we made a lithostratigraphic and morphostratigraphic Bayesian age model using OxCal, and then we combined that with a Monte Carlo slip rate model developed by Rob Zinke in order to be able to look at both the ages and the amount of offset back through time. And we reconstruct this kind of plot, and you'll see a few of these different plots. What this illustrates is that there are really very significant variations in the slip rate of the fault, and they are significantly greater than the uncertainty on the ages from the luminescence or the ambiguity of how much slip there's been from the geomorphic record based on the LiDAR. So we started off with Saxton River and published that. I think we then worked on the Clarence River and published that. And then we worked on Branch River and the Wairo Fault and another site close to Branch River that fills in the youngest part, known as Dunbeath. And this is the record from the Wairo. And you see it has some similarities with the last plot, but in detail, it's very different. So in detail, this one has a slow period from 4,000 to 2,000 years ago, though it was fast before, whereas this one has a slow period between 9,000 years ago and about 4,000 years ago. So they are slow and fast at different times. And in fact, it turns out that they're complementary. We didn't know this when we published the first records, and it started to emerge as we published the other records. So there are the two plots from those two sites down at the bottom right. And this is kind of a summary of our findings from this study. So the great thing is we can go to these sites and we can really choose where to dig a pit. And then within the pit, we can choose how many samples. Very different from doing radiocarbon dating, where it's very difficult to find material and one can only select samples where there happen to be preserved material, which, as I say, is very rare. So we've got these different records. Now, when we look at all four of the major faults, so the Hope, the Clarence, the Eritrea, and the Wairau, we see a pattern that's different for the different faults. And what's kind of very pleasing and somehow amazing, but perhaps not surprising, is that when you add up for each of the different intervals, what the slip rate is on that group of subparallel faults, they add up almost perfectly to a straight line, which is the black line on the diagram at the right. So these are the individual data from those four different faults. I haven't talked about the Hope fault. It's a very good record for a fast-moving fault, but it was largely based on radiocarbon. So it goes through landscape where there are a lot of bogs and opportunities for the preservation of organic material in a way that isn't the case for those offset records for the slower moving faults. But when we add these up together, produces this really beautiful straight line at about 30 millimeters a year, which is roughly 75% of the overall slip rate, which is up to about 40 millimeters a year across the plate boundary between the Australian plate towards the north and the Pacific plate towards the southeast. So one of the things about this adding up to a straight line is it really demonstrates the veracity of the dating approach, and particularly that some of the dates are radiocarbon and some of the dates are IRSL. So we were able to derive for this group of faults 25 slip rates in total. 20 of those were based on IRSL. It was about 90 IRSL ages, and it's only a subset of those that actually really constrain those slip rates. But of course, we didn't know which ones that was going to be until we dated them. So the dating of all of the samples from our pits is kind of still necessary, even if they don't, in every case, contribute to constraining the slip rate. All of those samples were measured with between 200 to 1600 individual grains. So if we add that up, it's a lot of work. And that one of the main time constraints on doing this work is just how long it takes to make the measurements. Now, what this tells us is actually really interesting, fundamental information about how faults work. These fast slip periods correspond to periods where temporarily these individual faults are weak, but they don't recover after one earthquake. They stay weak for between 3 to 5 earthquakes, allowing something like 20 to 25 meters of slip before they trade their slip onto one of the other subparallel faults. And so we can think of that as there being a kind of some mechanism that acts as a crustal strain capacitor, and the total capacity of the capacitor is something like 25 meters. And we have results that are rather similar, some of which are published already. Some of these from Dolan et al. 2016 in EPSL, and very much more recently, Dani Fougère, her results with similar IRSL dates that we measured in the publication Seismic had just come out earlier this year. And we're about to publish quite a lot more, by the way, from the Garlock. We actually have 200 age estimates at different sites on the Garlock, so we have a lot of information going back quite a long ways. Quite exciting. I think it'll be nice to see that when it comes out soon. Okay, now then, that's where things are working well. What do we do when the conditions get more challenging? And in some cases, they do get more challenging. For example, this is the site of McLean River. This is what it looks like more recently. It's aggraded by maybe 5 meters as a result of the Kaikoura earthquake in 2016. And the material is very, very coarse. And this is a landslide, just maybe 100 to 200 meters upstream of where the fault crosses. So at the location where we're really interested to find out what the slip rate is, there is just this huge input of very poorly zeroed, and it has almost no potential to have light exposure in this very short distance that it's being transported into our site. Here's another location. The Jordan thrust fault is just above here. Well, it would be, it's been eroded now. This is something like a 15-meter thick terrace unit, very high energy. You can see the large boulders down here. And this is a view along the Wairau River, and you can see these cobbles are about 20 to 40 centimeters on their b-axes. They're really quite large. So these conditions are really challenging. And what we've been doing is using MET IRSL. So MET stands for multiple elevated temperature. The minimum value of that to go beyond post-IRIR is 3 elevated temperatures, and we call that 3 ET. And this whole idea was started by Li Shenghua and Li Bo back in 2011. There's another paper, Fu and Li, where they really used the difference in the bleaching to do that. So this is really for the luminescence specialists. These are different protocols that we've been using. Really, all these ideas were developed by people like Tony Ryman, Remy Kars, myself and former student Chris Maguire, you saw a picture of him earlier, Rachel Smedley at Liverpool, Deborah Colarossi. Her work really informed us on how to tweak these to get better performance by following some of the advice that she'd made on trying to develop improved IRSL protocols. And this protocol on the right is what we've been doing most recently for our New Zealand project. We've got more results about to come out for those locations. We used a similar MET IRSL, actually with 5 temperatures to date this site. This is a site, a photograph of a site in Greenland, but its geometry is very similar to what there would have been in Derbyshire in England, about half an hour's drive from here, in about 24,000 years ago. And we were able to use this as a way to isolate stable signals that were well zeroed. So these results are in Rhodes and Lethard, came out in Quaternary Geochronology a couple of years ago. And these are some of the results from our New Zealand work using software developed by Andrew Ivester, worked as a postdoc with me and is now at the University of West Georgia in the USA. And these, you can see, these are just, instead of these just being IRSL age results for single grains, these are IRSL results where multiple different temperatures are providing agreement between those. So only those where different temperatures of measurement of the IRSL agree, that demonstrates that the signal was well bleached to a certain extent. Now, mentioning that, this technique actually allows us to determine actually how much light a grain was exposed to. And we've been using this, I mentioned Anne Guilles earlier, in some ways similar to the work that she's been doing, which is really exciting way that we can look to using luminescence to better understand sedimentary dynamics. And myself and Chris McGuire at UCLA back in 2000, we started in about 2011 or 12, I think, used this to try to get virtual velocities on the Mojave River running through the Mojave Desert. And more recently, we've been doing it on different samples from the UK. And my student, Tessa Spano, is just writing up her thesis now on doing this. It makes use of the fact that these different signals that we can measure have different sensitivity to light. And so this is an example from Tessa's work where we see single grain measurements of the response to blue light bleaching with blue LEDs in a RISO set with different prior blue bleaches by the same light source. So these are the kind of quantifications that we've been doing in order to try to understand how we can interpret those signals optimally to try to understand the sedimentary dynamics. This slide is one that's based on diagrams in Rhodes and Lethard from 2022. Jane Lethard was a master's student here at Sheffield. Now she works in the lab helping to prepare the samples. And what we noticed with those samples, really surprising result, is that something we call the burial bleach ratio, which is basically the slope of this line, which is the apparent age at different temperatures for individual grains, plotted as a function of the characteristic bleach time. For example, the time it takes to get that signal to 50% of its initial value. If we plot up the log of that value, it looks really, really similar to the grain size measured for the same sample. So we are effectively encoding information into the luminescence signals about the sedimentary dynamics in a manner rather similar to the way that grain size encodes information about sediments. Okay, so in conclusion, IRSL sediment dating gives us these opportunities to look at fault slip rates. And one of the things that we find is that many of these different systems, particularly where we have parallel faults, are exchanging fault slip through time. And that has significant implications for seismic hazard analysis and as well as understanding fault dynamics and fault physics. The chronology of this work, of any set of sediment dates, is optimal when we have enough data that we can really assess that. And another of my PhD students at the moment, Paula Bravo Rivera, is working on trying to see whether we can formalize some of those aspects. When we come to more challenging environments, we find that some form of MET IRSL can be useful, although note that it acts as a filter. So actually we reduce the number of grains that contribute to the age. And that means we have to increase the number of grains that we measure in order to get a statistically meaningful result. And we find samples where sometimes not a single grain was apparently bleached based on our expected age from other samples above and below it stratigraphically or morphostratigraphically. Apparently, it's so poorly bleached that we're not getting any grains that we can detect. We think that there is this kind of convergence between these different techniques focused at dating samples and techniques that are focused at trying to understand sedimentary transport dynamics. And I've been talking about faults, but actually there are many, many different geomorphic contexts, as well as other tectonic contexts that can benefit from this. Okay, that is it from me. So thanks very much. Thanks for listening. And thanks to all these funding agencies for these different funds that have in some way or other contributed to what I've been talking about. So thanks.
Thanks a lot, Ed. That was a really great talk. And now the chat is open for questions. So yeah, so before I have questions on the chat, I can probably ask a few of my own, and then probably things start popping up soon. But yeah, really interesting talk on the faults, especially in New Zealand. It's really nice to see how those sub-parallel faults are moving at different rates, but then they're converging to this uniform value. Just a quick question about that. The IRSL ages on all of those samples that were collected from there, they're all single grain ages?
Yeah, every one of those was single grains. And I think at Saxton River, we would actually have been okay if we hadn't done single grains, but we didn't know that until after we'd done the single grains, if you see what I mean.
Yeah.
And actually in New Zealand, using feldspar, probably small aliquots would also have worked quite well, because if the sensitivity distribution has the right properties, small aliquots give you results that are really very similar with single grains. The difficulty is, without measuring the single grains, you don't really know whether they have those characteristics. But if you have a machine that doesn't have the potential to do single grains, I think if you do single aliquots on the samples that look and feel most problematic, and you have sufficient sample numbers that you have samples above and below. Remember, it's extremely unlikely if a sample is poorly bleached that other samples in the same sequence are equally poorly bleached. They may also be poorly bleached, but probably not to the same degree. So you have the potential to determine, if you make enough measurements, even if they're not single grain measurements, whether what you're doing is at least internally consistent. And so I think actually, in retrospect, certainly at Saxton River, we would have been fine with probably even regular aliquots would have been enough to identify that. But we didn't expect such good zeroing there. And at some of the other sites, we don't. And at the more recent sites we're measuring, then certainly some of the samples have more challenging bleaching conditions, which is why we went to the 3ET technique.
Okay. So with that, you don't have the residual problem, or is that still a
Well, you
problem
may
with?
still have that, but the technique basically allows you to identify those grains where the signals that are harder to bleach are giving the same result as the signals that are easy to bleach. And that means it must have had enough light
Right.
to at least get
Yes.
those signals close to zero.
Yeah.
So that means that the result then, there can be other problems, but at least in terms of bleaching, we think that demonstrates that is what I call a meaningful age. Of course, you can also rework grains that are well bleached. So
Okay.
during that reworking, give them no light. So it still requires some interpretation. Anyway, we should
Yeah.
probably get to these questions that are pouring in.
Yeah. So, okay, I can just take the first question by Jing Tang. He says, great talk, Ed. How do you differentiate the contributions from the bleaching and fading, which may
Yeah,
both lead
so
to the
that's a
young
very good
ages?
question. And in fact, there is a paper in which I'm a co-author that was being published by my colleague Mark Bateman here in Sheffield. And we've just submitted the responses to reviewers' comments, and that will deal with this problem a little better. And I have to say, the straight answer is it's very hard. And I think we don't always know. We are now routinely measuring fading for every grain, but it's very, very challenging to get reliable fading estimates at the single grain level that have a precision that's good enough to be able to actually comment on that. I think the best answer is that in most cases of our experience so far, the fading is relatively rare. And so therefore, our way of identifying it is similar to, for example, intrusive grains and/or grains that fade that we see in regular IRSL. That is an anomalously young age, so for example, if a grain has come down a burrow or a root into a sedimentary body from the surface where it was zeroed more recently, it will give an apparently young age. And we don't actually have a way really to distinguish those with the grains that fade. In fact, that is something else that we're working on. So the simple answer is it's hard to distinguish, but the best answer I can give you so far, based on our experience in New Zealand and Scotland and California, is that actually those samples are relatively rare. Those grains are relatively rare. And if only one of the signals fades, for example, the lowest temperature signal fades, it's okay because the protocol automatically excludes it. So if it just fades a bit, then the magnitude of that fading is reduced in the overall age estimate by the others that fade less. So it's only if all three of your signals or two of them fade to roughly the same amount. So it's still an issue, but I think that it's not as big an issue as it feels like. Okay, we should look at Brian's question.
Great, Ed. Thank you so much. Well, we have another question from Brian Whaley that says, regarding other morphology settings, he has the same problem of dating the formation of block field in North Norway, but the rocks are ultramafic in the main. So what do you think about the possibilities of your techniques?
So I think that anything suggesting, if Brian, if you're suggesting that the block field is over 5 million years old, then or are you suggesting just that the bedrock is over 5 million years old? I'm not quite sure. If the block field is 5 million years old, that's probably older than we can do with luminescence anyway, particularly in hard rocks where the dose rates tend to be rather higher. And ultramafic rocks, of course, contain plagioclase commonly. Well, it depends how ultramafic they are. Yeah, if they're ultramafic, maybe they don't. So gabbro usually contains, metagabbro will contain plagioclase typically. So if we're not dealing with the age problem and just the dating problem, plagioclase also works with IRSL. It just suffers from the negatives more strongly than K-feldspar. So where we have both, we choose the K-feldspar, but actually plagioclase has the potential to be datable. But I would say it has a lower maximum age limit than K-feldspar typically, and it tends to fade more strongly. So you have to concern yourself with that aspect more so. But yeah, why don't you send me an email, Brian, and we can talk about it? That would be interesting.
Yeah. Okay, great. Thanks.
Good. Then we have another question from Paulo Figueiredo that says, regarding the K-spar grains used for the PIRI and other methods, based on your experience, do you have any advice regarding the density fraction that they extract to and the grain size that will be used for measurement?
Yeah. So grain size wise, we have something between wanting to use the modal grain size for that sediment. But in some cases, we are dealing with gravel, and clearly we don't want to use the modal grain size when we have a gravel, because that would be in the gravel size. If we want to do single grain IRSL, then we typically choose the grains that are between 180 and 212 microns. We have got some special holders for working on coarser grains, and we have, for quite a number of samples, sometimes worked on the 125 to 180 micron single grains without problem. So those grain sizes are our preferred grain sizes. So 180 to 212 as our preference, 212 to maybe even 300 is possible, and 125 to 180 is also definitely possible, and for some situations that might work well. In terms of density, we now normally use the regular alkali feldspar. I should really call it alkali feldspar rather than potassium feldspar. Density separation of 2.58. So we float off everything lighter than 2.58 grams per centimeter cube. And that includes the potassium feldspars and about halfway down. So we would actually get quite a lot of perthite, for example, that was roughly halfway between orthoclase and the sodium feldspar end of the plagioclases. But interestingly, at Branch River, when we did that back in 2012-13 with our first samples from that site, we had rather low yield. Very few grains gave us a bright signal. And I had the idea that perhaps if we looked just at the most potassic ones, we could increase the signal. And so we tried 3 different density separations at that site. And we did 2.58, we did 2.57 and 2.565, which is getting really, really close to the 2.560 of kind of pure orthoclase, if we can call it that. And we found a massive increase, an increase of about 1,000 in the total light count when we went to the what we called Super K density separation, that is using 2.565. And for a while we thought, oh, this is fantastic. For a couple of years, actually, we then prepared all our samples that way. But actually, then we met samples that didn't give us a good signal with that density separation, even though we had material. And however, when we widened it out to 2.58, we did have a good, bright signals that worked well. And what we think that was is that we had sanidine, which is volcanic potassium feldspar, being separated by our Super K or 2.565 density separation, whereas we were capturing perthite or something similar that was actually had a much brighter signal and was better behaved in terms of fading and those other kind of behaviors by doing the 2.58. So our normal procedure now is simply to use 2.58. But if we have sites with low yield, then we have we've done this very rarely, actually, because we have had very few sites with low yield. But then one of the things that we can try is making that density separation better focused at the most potassic end. I think it would also be possible to use 2.62 to 2.58. And, you know, when I was on my first sabbatical leave, which I took at the ANU and stayed basically with Rainer Grun before I was based there, which happened sort of 10 years after that. We had the idea that you could get fading isochrons. So in other words, you measure the fading for two different feldspar fractions. And in fact, it was the difference in the fading rate and the difference in the DE that gave you the apparent age that you were interested in. But since really working on feldspars, I find that the uncertainties would just multiply doing that. And so it's difficult to do that. I mean, I think it's still helpful to measure multiple different densities, so therefore different peak compositions. But it's not as rewarding as it might look like it could be on paper, is what I generally find. Great.
Thanks a lot, Ed. I will quickly go to the next question by Nasreen, who says that she recently started working on feldspar and was curious about why the protocol for feldspar doesn't include a cut heat, the same as that for a preheat as it does for quartz. Are preheat and cut heat similar?
Yeah, so I think that the answer comes down very straightforwardly, Nazreen, to that difference that I described in first order peaks and first order behavior versus this kind of flexible, very wide sort of behavior. So the function of the cut heat, that is the preheat that happens after the sensitivity beta dose, before the sensitivity measurement, is just to make a standard signal which is going to be the same every time that you measure it in your quartz. And it doesn't really matter whether it's the same or different from the preheat that you use. And if anything, it's better to have it less than the preheat so that you reduce the amount of sensitivity induced, dose-induced sensitivity change through the protocol. So that's why it's lower. But with feldspar, unfortunately, if you do it at a lower preheat, a lower temperature, or for a shorter time, you don't get the same population of traps contributing. And different feldspar grains will respond to that in different ways. And it's also possible that for a single grain, that the subset of grains which are giving you the subset of traps that are giving you a signal may evolve through the protocol. So that's why we use the same preheat in the first half and the second half of the SAR. It feels weird that we do it. I think that there was, when I started doing feldspar, I had the idea, which I think I'd heard at conferences and read in the literature, that there was much less sensitivity change. I don't actually really believe that. When I look at sensitivity change, there seems to be plenty in feldspar, but it just happens that using that same preheat seems to make the corrections adequately based on the fact that we apparently seem to be getting the right ages. So that's interesting.
Yeah.
Yeah. Thanks, Eddie. Thank you so much.
Thanks, Ed. There's a follow-up question by Jingtang, and he says, I always struggle to look for sandy lens for sampling in Piedmont fan environments. To your experience, do you think it's necessary to find lens with well-sorted sands or poorly sorted sands mixed with cobbles also work well with respect to bleaching?
Yeah, very good question. And so I would always take the sand lens in preference. So if I had a choice, I would go to the sand lens. And I've sat there, stood there, hammering a sample into a sand lens at a cliff in a quarry in Spain where there was 40 meters of vertical gravel above me. And I have to say, it really gave me made me go loose at the knees, the thought of it collapsing on my head. And that was a special situation where the gravel had been laid down over um, um, soluble beds that contained gypsum. So the gypsum had dissolved during oxygen isotope stage 6, and the river had continued to deposit into this developing hole and had built up 40 meters of gravel. So it's fantastic for the people who wanted to use the gravel for building highways, and it was pretty good for the sedimentary geomorphologists as well. So but in that circumstance or any other circumstance, if there is a sand lens, I would go for the sand lens. But I also think that it can often work fine if you can't do that. And we have different techniques for collecting the samples. One is to go along at night, and we call that scribbling. The other option is to do it under a black tarpaulin, or if you actually have a pit, you can do it under a piece of wood. So I've done both of those in the Mojave Desert. It's not very pleasant when the temperature is 110 Fahrenheit outside. It's usually significantly hotter under a black tarpaulin and or in a pit. Yeah, sort of doesn't feel ideal. But we've certainly done it at night. But in fact, we did 2 of the samples from Saxton River, that site where it all worked very nicely in New Zealand, by going at night. But it actually felt dangerous driving across the fan at night in the vehicle. I mean, we were unlikely to fall off a cliff, but we might well have damaged the vehicle by hitting a rock or dropping one of the wheels. It was really difficult to see. And actually that night it rained as well. So everything about it felt a bit negative. So what we usually do is try to find a way to ease the sample into the sandy gravel behind a large cobble. And we got really good at doing that. So we find if we dig a slot forwards into the gravel, and then a second slot at 90 degrees at the sort of halfway along that slot, and put the sampling tube parallel with the surface of the pit, sort of it's like a dog's leg, a letter L that you've dug of tubes, and then knock it sideways. The cobble that you're behind has the freedom of movement to move forward towards you. And as you're holding it with one hand, hitting it with a hammer with the other hand, you can actually control that cobble with your left foot. And me being right-handed, you could do it the other way around perfectly well as well. And that allows us to keep it dark and fill the sample with a gravel. I think that's actually recorded. I think we wrote that protocol down in the Rhodes and Walker chapter in the book. It's an edited book put together by Mark Bateman. I think it's called Luminescence Techniques. So yes, my preference is always look for the sand lens, but I don't give up if I don't find one. The sand within the gravel usually gives me a date. It's just harder to sample and it's harder work. I often have to measure more grains. Okay.
Okay, thanks a lot, Ed.
I'm running over time here.
No, it's been a great couple of questions, and thank you so much for answering them. Yeah, we are up for time, so I will save the rest of my questions for some other time. Yeah, probably next time that I see you. So yeah, thank you for coming here and giving a talk today. It's been wonderful to have you here.